I have the pleasure to introduce our next two speakers. Our first speaker is Professor Rob Ritchie. He's a distinguished professor of engineering from the University of California at Berkeley, and he has been working a long time on the subjects that he will talk to us about: biological and structural, he wrote, mechanical materials. So.
Well, thank you, Leslie, and thank you, Professor Sagnet, for inviting me here. It's an awful long way from California, but it's been worth it. So, I'd like to talk this morning about my favorite topic, which is damage tolerance, and I'd like to look at a number of different classes of materials where we've tried to enhance damage tolerance, which is basically fracture resistance coupled with some degree with strength. So I want to look at some biological materials. I'm not going to talk too much about this because there's not much biological work in this conference, but I would like to mention a few materials first, and then I'm going to talk about some metallic materials and some of the more modern metallic materials, to coin a phrase, these multi-element metals. So this is my outline. I want to say a few comments, first of all, about toughening and what I understand by fracture resistance in materials, and then take you through something which is probably quite close to you, which is your skin and your bone. I'll have a little short detour via fish scales, and then I'd like to talk about these new, not so new perhaps anymore, multi-component alloys, mainly bulk metallic glasses at high entry alloys. So first of all, what is damage tolerance, and what do we understand by this? And it's, as I said, it's a combination of fracture resistance, toughness, and strength, which is generally a compromise or a conflict, as I've called it. There's a conflict between strength and toughness. Most strong materials don't necessarily excel in toughness, and vice versa. And there's a number of conflicts in this whole aspect of fracture, and I like to, this is something I always talk about, so if you've heard this before, you can probably leave the room, but I think of fracture as a mutual competition between classes of mechanisms. They're what I call intrinsic mechanisms ahead of the crack tip, toughening mechanisms, and these are mechanisms that basically inhibit damage, whatever that may be, void growth, particle fracture, and so forth. And the prime factor here is basically plasticity. There are other things, but that's the prime thing. And these mechanisms take place ahead of the crack tip, and they really are how metals or ductile materials are toughened. But those mechanisms simply don't work when you get into a brittle material like a ceramic. And then there's another class of mechanisms that operate behind the crack tip or at the crack tip. And I call these extrinsic mechanisms, and these are not associated with plasticity necessarily. They're associated with shielding, and they effectively lower the local stress or strain field at the crack tip compared to what you think you have. And there's a number of mechanisms. Bridging is one, of course, as we see in fiber composites and lots of different materials. Crack closure, which is a wedging mechanism, is seen in fatigue, and deflection. Now there's interesting contrast here. These mechanisms, these plasticity or intrinsic mechanisms, originate typically around the nanoscale, but these mechanisms can operate at any scale. In fact, in bone, we'll see that these mechanisms operate on the scale of hundreds of microns. These are a property of the material, and these depend on the geometry of the crack and so forth. These mechanisms have simply no meaning for initiation. You have to have a crack to have an extrinsic toughening mechanism, so these only operate for crack growth. And what's interesting about this is that these mechanisms, although plasticity is the same thing, generate the so-called R curve. We've heard about that the last few days. This is sort of a toughness parameter as a function of crack growth. And the R curve is absolutely fundamental, in my opinion, from the perspective of damage tolerance. You don't want things to simply break catastrophically. You want them to be able to tolerate damage, and damage means slow crack growth in many cases. So the generation of an R curve is extremely important. Now, as I said, there's a conflict in many materials. Toughness and ductility don't always go with strength. These are mechanisms that predominate in brittle materials like ceramics, these in metals. Yet biological materials do a very good job, a much better job than we do in balancing these properties, and in many of those materials you'll see both these classes of mechanisms operating at the same time. So, biological materials first. Now these of course are characterized by multiple length scales. You've all heard of hierarchical structures and so forth. And there is structure scales from the atomistic all the way up to the macro scale. So we have to have means of looking at this, and I use a number of techniques I'll talk about today. With the macro scale, we use fractional mechanics, of course, and then we do a lot of in situ testing in the SEM, and I'm not going to talk much about in situ tomography, but this is at the micron scale. We'll talk a little bit about small angle X-ray scattering, which is a little bit lower than that, and then of course down at the nanoscale we do now quite a lot of work in various TEM and STEM techniques to try and look at mechanisms. So that's our sort of scale of techniques over these length scales. So to start with, let's talk about bone. Bone is a pretty complicated material, but it's a rather remarkable material, and of course it does have a lot of length scales. A simpler way of looking at this perhaps is to go to what Danny Wilder and Weiner did a few years ago, the sort of 7 hierarchies of bone. Down here we're talking about collagen molecules that are twisted together to form collagen fibrils. This takes us into the submicrons from the nanometer stage. These have minerals deposited on them, apatite at a fairly regular, I think it's 64 nanometers apart. These are the fibrils. The fibrils then are twisted into fibers. We're now up into sometimes called the mellobone regime. We're in the tens of microns now. And then we go up into the hundreds of microns, and we have these so-called osteons, which contain the Haversian canals. These are concentric structures. The interior carry the blood vessels, and the bone remodels that way. And this has characteristic length scales of hundreds of microns. And then up at the top here we have the bone itself, and of course there's the compact or cortical bone on the outside, and the trabecular or spongy bone on the inside. So it's a whole range of length scales. Now how is bone toughened? Bone's a pretty resilient material, and this extrinsic-intrinsic notion works reasonably well. If you look at mechanisms below about a micron, we talk about this being ahead of the crack tip. It's plasticity, and plasticity in bone is a variety of mechanisms, but the principal one that is most common is the fact that you've got collagen, and the collagen simply stretches, and then it tends to slide apart, and we have something called fibrillar sliding, which is just the sliding of collagen molecules next to each other. That's a plasticity mechanism, but if anything stops that, if anything locks that up, that's how you lose ductility in bone. So the toughening mechanisms in bone at these sort of scales are plasticity, and the plasticity is predominantly this fibrillar sliding. But then if you move up in scales to around way above a micron, and then you look behind the crack tip, you see mechanisms that you'd see quite readily in a ceramic. There's a lot of microcracking in bone. It's very important. It leads to remodeling of bone. It also is a mechanism it's an inelastic mechanism, if you like, of sort of pseudoplasticity. But cracks then grow into this sea of microcracks, and little regions in between those microcracks are bridges, and then you get very strong deflection. These columns here are the so-called osteons. These run along the axis of the bone. These are Haversian canals inside. The boundaries of these osteons, this is how bone remodels, tend to have a higher mineral content, and cracks will tend to deflect along those boundaries. So if we look at a typical example, this is tomography. I can show some examples of these mechanisms. This is a three-dimensional tomography of bone. This light blue is, of course, the Haversian canals. This white area is the crack. This is the front of the crack here. And these dark blue areas behind the crack tip are these regions of uncracked ligament bridges. And then the deflection one is very shown here. These are the osteons, these yellow columns. This piece of bone is being pulled vertically, so the crack should propagate, behave itself perpendicular to the maximum tensile stress. But you can see in the white area that the crack deflects dramatically as it encounters these osteons. And the deflection actually is more than an in plane. You get twist as well. So there's a lot of toughening associated with these extrinsic mechanisms, in addition to the classical plasticity mechanisms at the smaller scales. Now, how does this affect bone's properties? Now, I've got many examples. This is an old one. You may have seen this before, but it's an easy one to look at. I've looked at various diseases. We don't always understand the biological source of those diseases, but we can see why it affects bone. This is one that's close to my heart. It's when you start to age, you have a higher propensity of fracture of bone. A lot of that's thought to be due to loss of bone mass, which is a bone quantity issue, and it of course is, but there's also a bone quality issue as well, which is the fact that the bone deteriorates in its toughness. These are R curves. This is young bone, 30-year-old, 50-year-old, and 80 to 90-year-old bone. And you can see as you get older, you don't see this very clearly, but there's a deterioration in the initiation toughness of bone here, and there's a great bigger deterioration in the crack growth toughness. So why is that? Well, just quickly, you can again subdivide this into intrinsic and extrinsic. Extrinsically, you see these little uncracked ligament, these little uncracked regions that act as bridges. Their spacing is typically the spacing between the osteons, because that's where the microcracks will form in those mineralized boundaries. But if you look at the piece of young bone versus a piece of old bone, this is tomography, you see these sort of blue and green columns are the osteons, and what you can see is there's a dramatic increase in the density of osteons as you get older, particularly if you have excessive remodeling. And since these little bridges are a function of the spacing of the osteons, what happens as you get older, this bridging effect is much less effective. So there's a deterioration in the crack growth toughness. The intrinsic part is interesting too. We can look at this. We do this in the synchrotron. We do a tensile test on a piece of bone in the synchrotron, and we're measuring here the strain in the bone. And we then do wide-angle X-ray diffraction, which is focused on the mineral, and we can get the strain in the mineral. That's not too important here. But we can also do small-angle X-ray scattering and look at the collagen. And since the mineral is very uniformly placed along the collagen, we can get a strain there as well. We can measure the strain in the collagen. And what you find is that if you look at, this is the strain in the collagen, this is the strain in the bone itself. For young bone, let's say about a 1% strain, you can see virtually all the strain is carried by the collagen, of course, because that's the flexible part of bone. But if you look at old bone, it's a very different story. Now, for a 1% strain in the bone, half that strain is carried by the collagen. So the collagen is less effective. And what basically happens is, instead of sliding apart like this, it locks up. And it locks up because of cross-linking. Your collagen has many types of cross-links in bone. These are called non-enzymatic cross-links, and they basically lock up the process. And it's just like an embrittlement in a magnet. You just lose ductility. So those are, again, these two different classes of mechanisms. They're very different. They operate at very different scales, but they all affect the toughness. This is an example of this from a problem with use of bisphosphonates. These are used, they're widely prescribed to deal with osteoporosis, particularly in women, and they work by limiting bone absorption, but a small portion of the population suffers these called atypical femoral fractures. They get sudden breaks of their femurs. Relatively young people get this if they've taken these drugs, and it only accounts for about 0.2% of the population who take these drugs, but it's such a critical fracture that the use of bisphosphonates has dropped dramatically in the last 10 years because of fears of this. And this is a great change, because these are good drugs. So we've been trying to understand what this is caused by. you'll notice this fracture is very, very clean. If you broke your arm now, you'd have a really jagged fracture as the crack tends to deflect along the osteoidal boundaries. This is very, very clean, and we've just recently been able to get bone from people who've suffered these fractures, and you can see what happens here. Regular bone, you get the deflection. You see a crack's growing this way, the osteons are this way, and you see the crack tends to deflect. This is a very common thing you see in healthy bone, but in these people who are prone to this problem, the cracks just simply don't deflect. So there's something associated with an abnormal mineralization. We also see excessive cross-linking. This is the cross-linking in bisphosphonate-treated bone. This is regular bone. So there's also a loss of ductility. But again, you can see there's these two contributions to the problems of toughness. And this is not unusual. We've looked at things like osteogenital imperfecta, which is brittle bone disease in children. We've also looked at vitamin D deficiency. And these sort of notions of a lockup of the collagen plasticity and the change in the deflection path of the crack are quite common in showing that these diseases cause bone fracture. Now, why the biological part behind that is much more complicated, of course, and that's not very clear. But these simple mechanisms associated with fracture seem to apply very well in bone. Now, looking at something different, this is skin. And if you're a fracture person, skin, and there's a bit of fish scale here, skin is not a very good material because it's almost impossible to break. You just keep pulling it and pulling it and pulling it. This is a piece of rabbit skin, and it's very difficult to break. In fact, there is a hang glider in America who jumps off high mountains, and he has his wings attached to his skin. Not a harness, but attached to his skin. So skin is a pretty complicated material, but you can see with these sort of pictures here how it's, as I said, it's almost impossible to break. Whether you have an internal or an edge crack, it just doesn't break. So why is that? Well, if you look into the many layers in skin, but the dermis layer consists of these collagen fibrils. Now, they don't have mineral, they're generally just pure collagen, but they're long and they're twisted and they're curved. And when you pull skin, we put this in the synchrotron and we can watch the movement of the collagen under load. You get a series of processes. The collagen is sort of a bit of a mess to begin with. It's all tangled. And as you start to pull it, it will first of all start to rotate. It then starts to straighten. It uncoils here. It'll then sort of stretch apart. And then finally, if you pull long enough, it'll break. And we can watch this in real time. Just to make a long story short, these are sort of images. The collagen in skin looks like this to begin with, and when you've really broken it, it's fully aligned like this. So these are very effective mechanisms for absorbing energy and increasing the tear resistance. Now it's funny, these fish scales are kind of similar. We've also looked at fish scales. These are not pure collagen, they have mineral in them, but a classic armor will have a very hard surface which resists penetration. But if the whole material was made of that, it would just shatter. So there's generally a softer but tougher sublayer or inner layer, which then accommodates the extra deformation. And in biological materials, this is just changing the mineral content. It's more mineralized on the surface than it is in the interior. And biological materials always do gradients very well, and they morph out any sharp interfaces. So there's a beautiful gradient in mineralization as you go from the hard surface to the subsurface. This is the arapaima fish. It's an enormous fish in the Amazon, and its predator, of course, is the piranha. I work with a mad guy called Mark Myers, who some of you know in San Diego, who goes fishing and swimming in Brazil and catches piranhas and brings the teeth back. And we use that as the penetrators of the skin. This is a picture of what happens when you put a piranha tooth into the skin. But what's interesting is that it breaks the core sometimes, but the inner layer is extremely tough. And how does that work? Again, we put this in the synchrotron. And what we find is that the collagen will simply rotate to carry more of the load. It's a beautiful mechanism, and we can watch this in real time. These structures tend to be what's called Gouligan structures. They're like a spiral staircase, and they will simply rotate. These are the ones that are closer to the tensile axis, and they'll carry more of the load. And there's some fish that have double Gouligan structures, which are even more complicated. Very, very interesting. Anyway, that's the way that collagenous materials and mineralized collagenous materials tend to develop their damage tolerance. Now let's look to something very, very different. Let me look now at metallic materials. And the ones that I'm interested in are some of the, dare I say, newer ones. These are multi-element materials. Now, the one that's been around the most is so-called bulk metallic glasses. These tend to have many elements in there, and the notion they form a glass is because of the so-called fusion principle. Each element has a different crystal structure, perhaps, and when they're all together, they get confused, and the kinetics are slow, and you can make a glass. Now, this is one of these materials, and we think of glasses as being fairly brittle, but these are obviously anything but brittle. So glasses have a problem, these metallic glasses have a problem, in that they form shear bands, and in many glasses, you form a single shear band, it zips across the material, the thing fails in near zero strains, and the toughness is down to 1 or 2 megapascal root meters. So that is obviously not a good thing. But it turns out that if you can distribute and have multiple shear bands, this is the basis of plasticity in these materials. So a single shear band will kill you, but multiple shear bands gives you plasticity. Now, metallic glasses tend to have very high strengths. They're almost near theoretical strength in some cases. So if you can get plasticity, which generates ductility, not much, but enough, you can generate toughness. So the key to metallic glasses in getting a damage-tolerant material, you've already got the strength, you want to get plasticity, and in a simple terms, that's promoting multiple shear band formation. Now, how do you do this? Now, I worked with Bill Johnson, who was, of course, one of the pioneers of metallic glasses, and what he came up with this idea of is if you could block the shear band, you could block a shear band, then more shear bands would form. So he developed so-called glassy composites. He put a second phase in. It's a dendritic phase. It's not even crystal. It's not even amorphous. And the idea was that you match the spacing of this phase so that the spacing of these second phase in the glass is smaller than the critical crack size to cause failure in the glass itself. You're matching the mechanical and microstructural size scales. And in doing this, we did the toughness measurements for him, and we get very good properties. The typical glass, this is vitriol, the first ones that came out. It has a toughness of 50 and then it breaks catastrophically. A lot of golf clubs were made of that, and a lot of golf clubs fractured catastrophically. But these ones show very strong R-curve behavior. This image here was one of these glass composites, and we're getting toughnesses of around 200 at the best with strengths over a gigapascal. These are very respectable. There's a couple of things you need to do. You have to have the second phase, as I said, the spacing small enough so you can't see that size in the monolithic glass. You have to have the shear bands intersecting that second phase, so you need to have a low modulus, because of course cracks will tend to follow a low modulus phase. And then you want them to arrest and not penetrate the second phase. And if you look at sort of the He-Hutchinson plot of a crack penetrating or arresting at a dissimilar metal interface, it's a function of the elastic mismatch across the interface, which is simply the difference divided by the sum of the respective moduli of the two materials. This is the first Dunder's parameter. And on this axis, it's basically the interface toughness divided by the toughness that the crack is going into. You want to be in this region here for the crack not to penetrate. You want it to arrest or go around the particle. And so to get in this region, you want the Dunder's parameter to be close to 1, so you want the stiffness of the second phase to be as low as possible. And this was this made very good materials, and in fact they're being used by NASA a lot now. The guy who did a lot of the work was Doug Hoffman, who of course works with NASA. We wondered if we could do this in a monolithic material too, and this is one of the toughest monolithic glasses. We went back to a very old, very sort of hand-wavy attitude notion, which is the Pew ratio, that if you had a high bulk to shear modulus ratio, low shear modulus would give you lots of shear bands, but a high bulk modulus would prevent them from opening up to form cracks, which is basically saying we want a high Poisson's ratio. We made one with a palladium containing glass. It's obviously not very practical because palladium is about $1,000 an ounce. And we made this material, and it was remarkable. You saw by the image, you get very tremendous ductility. We got a bending strength here of 2.5 gigapascals, and we did toughness tests on this, and we got R curves with toughnesses up to 200 megapascal meters. These are enormous, 2.5 gigapascals and 200 MPa meters is an enormous damage tolerance. And if you look on an Ashby plot, this is the toughness versus yield strength. We're right along here. We're right on the limit of the best there is, and this is these metallic glasses, composites, and this particular palladium glass up there. We got the front cover of Nature Materials for this. It was very interesting. The paper was called a tough glass, and we got lots of people calling up, and my favorite phone call came from Ferrari, who called up and said, we saw your paper on tough glass. We think this would make a wonderful material for a windshield. And I said, yeah, it's got all the properties you want. There's just one small problem. Of course, it's not transparent. So everything was good. We thought we'd conquered the world. And then we started to get more of this palladium glass. We got some from Germany. And we'd measured this very, very high toughness of 200 MPa. And then we started to measure somewhat larger samples. And we started to get toughnesses were a little different. We got down to 20 MPa root meters. So this is variability in the toughness, but it's huge variability, varying from 20 to 200 in the same material with only a small change in the size of the sample. So we've been interested in this. There's a lot of variability in the toughness measurements of metallic glasses, mainly because they've been badly measured. So there's a lot of people who do notch effects. They measure the notch apparent toughness, and the notch root radius versus the apparent toughness is a very strong effect, much stronger than in regular materials in these glasses. And these are sort of fictitious numbers. So it elevates the toughness erroneously, and people like that. But if you measure it properly, and we try to measure it properly, this is looking at quite a common glass, Fitzroy 1 again. This is the toughness as a function of the ligament size. This is basically the size of the sample. This pertains to small-scale yielding, whether you have a K field or not. And if you're measuring in a linear elastic regime, in the relatively less tough glasses, everything's fine. The toughness, as you might expect in a crystalline material, doesn't vary with the size of the sample. But as soon as you get out of that regime into the so-called non-linear elastic fracture mechanics regime, where J should apply, instead of getting a number in terms of J, which is constant, you just get this massive scatter in the data. And this is, as I said, it's almost an order of magnitude in the variation in toughness. Now, why is this? Well, this to me is very similar to the old story when J was first developed. We have John Landes here. He did this. They were interested in looking at two very extreme geometries, the so-called tension, center tension versus the edge crack bending. These fields are unique under linear elasticity, but if you're in slipline fields for non-hardening plasticity, they're completely non-unique. And the reason that J works, of course, as a means of measuring beyond the linear elastic regime, is that there's, within that, locally at the crack tip, you get this so-called HRR field, which is a power hardening field, which gives you some uniqueness. The problem with metallic glasses is they don't have local hardening. In that little zone ahead of the crack tip, you don't have enough power hardening, so there probably isn't very much of an HRR field there, and the old notion of slipline fields is a pretty accurate way of looking at this. Even tensile tests in these glasses are very, you probably not see this, this is one for bending, this is one for tension, they're very different. So we think that basically it's going to be very difficult to get reproducible numbers in metallic glasses once you get to tough glasses, because the range at which the J approach to non-elastic fracture mechanics applies is very small, perhaps even non-existent. And there's a more interesting reason, which I think is more fun, and that is that I think the community now realizes that the amorphous state, the glassy state, is not a single state. That there is some degree of local order in that amorphous state. Now, people like Lindsay Greer talk about nanostructure in the amorphous glassy state. We tend to talk about local configurations or motifs of atoms that form in local order. This is basically local, short to medium range order. And most of the most stable forms of these kind of motifs have icosahedral symmetry. They have five-fold symmetry, and they're generally most stable. But there are some configurations that are not as tightly packed, that don't have as much icosahedral symmetry, and these tend to be relatively unstable. And Evan Maher has coined the term geometrically unfavorable motifs, gums. And these are local order which is not quite as stable. And if you do that, this is all done by MD and DFT calculations. If you do these calculations, we find that 82% of the atoms involved in shear transformations, that's the shear bands which cause the plasticity, which is the essence of toughness in these glasses, are associated with gums. So I liken this to you basically discovered the equivalent of grain size in an amorphous material. If you can build in a homogeneous or a wide distribution of these gums or less stable local symmetry, you can generate not a single shear band, which gives you very low ductility, but multiple shear bands that gives you plenty of ductility and toughness. And these things can be changed by composition. You can change them by increasing the cooling rate. The higher the cooling rate, the more likely you are to get this unstable local symmetry regions, which can trigger shear bands. So it's a very nice theory, but it's a theory. How do you experimentally prove this? It's so, an MD calculation or PFT calculation is at some ridiculously low temperature and very high strain rate. It doesn't necessarily appeal directly to reality. So can we actually see this can we prove this experimentally? So people have tried to do this. You can get diffraction patterns from these different local regions of symmetry. But if you try to map them across a large region, you're looking at a very small region with high resolution, but you want to map over a large region, there's problems. It takes too long. You tend to damage the foils. You can get drift. And so we've come up with a new technique. This is being done at the National Center for Microscopy. I'm working with Andy Miner there. And we call this nanobeam scanning, nanobeam molecular diffraction. Basically, we scan small regions. They're about a nanometer square region, a little column, about 50 atoms in each little column. And it's, that's sort of short to medium range order. And we take a diffraction pattern and we move on and we start moving through the structure. But we can do this extremely rapidly. We have extremely fast detectors on our TEMs now, which can look at 400 frames a second. And within the next year, we'll be up to 100,000 frames a second. So we can look at these little small regions, map out the order if it's there, and then move through large areas of material. We can also, at the same time, measure the local strain. So we can get the icosahedral symmetry and the strains for each region at the same time. So there's a chance here we might be able to put two and two together and show that these gums are the essence of plasticity against toughness of these glasses. This is the first sets of data we've generated. It's still rather in its infancy, but what you're seeing here is a little piece of, it's a simple glass little region here, and we've scanned across here. And the colors here, the redder the color, you're seeing a local region of two-fold symmetry, three-fold symmetry, four or five-fold symmetry. So we can start to map out the local order with this technique. This is the first one we've done. And we've also tried to relate this to shear bands, and this is a process that's still being worked on. We have a sample with a hole in it in the high-resolution electron microscope. It's pulled, and we are able now to map out both the strain and the local symmetry. Now this is the DFT, which is always very clean. You can see the strains generating out from this hole as being loaded this way. And the darkened regions here give you regions of lower icosahedral symmetry. Those where the gums are, which we think are the essence of what forms shear bands. So that's what the DFT shows us. And these are our images. This is the first one we've taken. You can see again, not all are very clear, but this is indicating the regions of the shear strain here, these yellow regions here, and this is looking at the fourfold symmetry, the local order, and you can see, we can start to see regions in the same location where we're getting a reduction in the local symmetry. So the tie-up here is that where we're having shear band formation can be associated with regions of less icosahedral, less stable local order. So it's, I mean, we're not there yet. This is kind of a chicken and egg argument here, but we think we can put the two together and get experimental verification that this is the essence of building toughness in glasses by generating less stable local order. So let me finish by talking about high entropy alloys. These are probably the hottest thing in metals these days. As you probably know, with high entropy alloys, they are alloys with multiple elements. Typically, when there's more than about 5 elements, the original concept was that configurational entropy would overwhelm the enthalpy of phase formation, and we'd end up with a single phase material. Now, we don't think that's true anymore, but the alloy that's closest to this was done by Ye initially in Taiwan, but my buddy Brian Cantor in England also was trying to do this. He didn't coin the term high entropy, but he came up with what is now being known as the Cantor alloy. This is a chromium manganese iron cobalt nickel system. Variety of crystal structures there, but it forms a single phase FCC material. This is probably the most popular high entropy alloy. A lot of work was done in China and in various places for 10 years or so, but then Iso George at Oak Ridge got involved and started to make very good material. We got access to this material, and this is quite well known now that this material, this Cantor alloy, has pretty good properties at room temperature. It has a strength of about 800 MPa and a ductility of the order of 50 or 60%. But what's remarkable is that everybody knows now that when you go down in temperature, it gets, from room temperature to liquid nitrogen, it gets 70% stronger. Well, that's pretty obvious. But it also gets 25% more ductile. So we measured the toughness. Now we're in the intrinsic region now. This is all ductile fracture. We measured the toughness of this. These are JR curves. These are all valid toughnesses, and we got these amazing toughnesses of more than 200 megapascal root meters at crack initiation, at room to liquid nitrogen temperatures. And the crack growth toughness, which is perfectly valid in this size of sample, was up around 350 megapascal root meters. And these are enormous numbers. You look at the structure, and at liquid nitrogen temperatures, you see a lot of twinning, nano-twinning. And this is really the key here, this steady strain hardening in these materials. The hardening, of course, is good for hardness, but the strain hardening suppresses necking, so we get good ductility too. So we looked at this because the room temperature properties are pretty good too, and there's no twinning there at room temperature in this alloy. And this was done, we looked at TEM studies. This was done by a colleague of mine, Yu Qian, in Zhejiang University. These particular alloys, as you probably all know, have fairly low cyclical energy but high friction stress. If you do a fracture toughness test in the TEM, which is not really a fracture toughness test, you see lots of partial dislocations zipping out from the crack tip with their trailing partials and a bit of cycle in between. But you see a duality of toughening, of deformation mechanisms. You see these long planar slip bands where the undissociated dislocations move in very tenuous fashion, yet you also see this very rapid motion of the partials. I'll give you an example here. This is that same slip band, and I'll stop the movie in a minute. These perfect dislocations are moving very slowly, but you'll see a partial dislocation move in like grease lightning next to it. So again, you can see the slow movement of the, there's the partial coming in very, very rapidly. So we have a duality of mechanisms. We have a ponderous movement of the undissociated dislocations that provide strength. We get the rapid motion of the partials that give us ductility. There's also very strange three-dimensional defects. We call them stacking for polyhedro parallel pipe bonds, which tend to arrest a dislocation motion. And we also see something which is very interesting. We see bridging these materials. If you look at the crack tip, you see these little nanoscale bridges that form across the crack, and these are actually twinning as well. Now this could be an artifact. This could be an artifact, but it's still very, very interesting. Just quickly, we've also took elements out of these materials, and we've taken, we took two of the elements out to have a cobalt chrome nickel material, and it's even tougher and stronger. Its strength is now up to about 1.4 gigapascals, and it has 90% tensile ductility at liquid nitrogen temperatures. So this material is harder, it twins at room temperature. You can see the twins in a simple microstructure here. When you do the toughness test, the numbers become almost absurd. The initiation toughness is well over 200 megapascals. At liquid nitrogen temperatures, it's 270 megapascals. And the crack growth toughness in valid ASTM is 450 megapascal. These are enormous numbers. And we see it's got very low stacking energy, it has great twinnability, and you see these, again, a duality of mechanisms. There's a twin structure throughout. The twin boundaries will effectively arrest this dislocation's motion. You can see one coming up here. But the boundaries also are highways by which dislocations can move fairly fast. This is basically looking at a twin boundary, and you can see these dislocations moving along the twin boundary quite rapidly. Again, we have a duality of mechanisms: arrest of dislocation motion and rapid motion. We've done these experiments at liquid nitrogen temperatures in the microscope. Not quite liquid nitrogen, but this is basically at 93 Kelvin. And again, you can see the rapid motion of dislocation along the twin boundaries. And just to finish, why are these materials so unique? And we don't think entropy is so important, but we also think that local chemical order is important too. We've done a number, again, this is all in the realm of DFT or MD calculation. We've done Monte Carlo DFT simulations where we've taken a random solid solution for these alloys and then started to put increasing degrees of local order in. And what we find is that there's a dramatic effect on things like the stacking energy. Stacking energy can vary by up to 70 megajoules per meter squared, change in the twin boundary energies, and a change in the energies for interstitial formation. So we think also that local order has a big effect in these alloys too. No one's seen it yet, very little evidence, but we think that's important too. So let me finish just by showing you this plot again. These multi-element metallic alloys have a remarkable damage tolerance. The glasses have the highest strength. The high-entropy alloys seem to have the highest toughness. These cobalt from nickel. And we think in both these cases the notion of local, medium, short to medium range order has a very important effect on development of these materials. Thank you.
Those materials for those high entropy alloys?
You know, this is one of the most difficult questions to answer because in structural materials, unlike electronic materials, there's generally a couple of decades time lag between developing them in the laboratory and putting them into reality. We're just putting ceramic composites into aero images now, and they were developed 30 or 40 years ago. So, but these high entropy alloys are relatively normal materials in terms of how you process them. You can make them involved. They're not little tiny bits of glass like the bulk-type glasses are. So there's a very good chance they'll find a lot of applications. These have particularly good cryogenic properties, so they might be useful for tankage and pipelines. There's other people looking at high temperature versions of these alloys, not this composition. And there are, we think of 50 elements in the periodic table, there are 9 million of them out there, and if you start changing to make equiatomic compositions, there's an infinite number of alloys. This is relatively conventional materials, so they should find out.